3 blocks are at rest on a frictionless horizontal table with M1 equal to 8 kilograms and M3 equal to 9 kilograms. We don't know what M2 is, but there's a horizontal force of 108 newtons applied to block 1. The acceleration of all blocks is found to be 3.4 meters per second squared. And we want to find the middle mass. And then find all the normal forces between the blocks. Alright, so first thing I would do is redraw the problem and decide what is going to be the system that I'm analyzing, because it's my choice. I could make this system anything. So I'm going to make the whole thing the system. And you put the dashed boundary around your system to make it clear what the system is. Then we want to create what's called a free body diagram for the setup. Free body diagram shows the forces involved. So there will be a force pulling the blocks down. That's a force due to gravity. There would also be a normal force holding them up. That's a force from the surface of the ground. And we have this force of push. That is the reason for the acceleration, because that's the unbalanced force. So what I would do first is find the total mass of this setup, because using Newton's second law, we would know the acceleration and we know the force applied, so we can find the mass. Force applied is 108 newtons, and I'm going to call this the total mass of the whole thing. Alright. And it'll be M total equals 31.7 kilograms. Alright, now we could use the idea that M1 plus M2 plus M3 is how we get the total mass. So we could certainly plug in to find M2. M2 is 14.8 kilograms. Alright, now we want to find several normal forces, they're called. These are forces from one surface on another surface. And to do that, we have to draw the problem again, but make a different choice of system. Alright, so I'm going to redraw it. But this time, I'm going to let the very last block be my system. So now I'll draw a free body diagram just for that block. Now it's going to have a weight and a normal force, but those don't really matter when it comes to analyzing the lateral normal forces. So I'll just leave those off. What I really care about is the fact that there is a force on this block, pushing it to the right. And it has a name. It would be F of 2 on 3. Now that's going to be the only net force on that block, because there's no friction involved, they said, in this problem. So we want to apply Newton's second law just to block 3. So you'll have F net on 3 equals the mass of 3 times the acceleration of 3. So Newton's law is very versatile because you can apply it to whatever system you choose. And we know what the mass of 3 is. Block 3 has a mass of 9 kilograms. And it's going to have the same acceleration that all the other blocks have, which is 3.4 meters per second squared. Alright, that comes out to 30.6 newtons. Alright. So now we know this is 30.6. And so the thing about Newton's third law is that forces come in pairs. So this guy has to have a pair somewhere. And so where is his pair? Well, whatever object is pushing on block 3, that same object is going to feel a push back by object 3. And so the thing that's in contact with block 3 is block 2. And so if I do a free body diagram for block 2, maybe I'll do it up here, I'll find that block 2 feels what's called a reaction force in an opposite direction but with the same magnitude. And so whereas this one over here is F of 2 on 3, this one's going to be F of 3 on 2. Alright, so I would redraw the system. And this time we'll make a different choice of what we want to analyze. And so well, first of all, let's just put in that this is 30.6. All right, now what choice of system would be good? I'm going to actually analyze the last 2 blocks now as the system. So I can do a free body diagram for both of them at the same time. And what force are they feeling? Well, those 2 blocks are pushed by somebody. But who pushes them? It's actually not going to be considered the person who's applying that force, or the person or machinery or whatever is applying that force. That's not who's pushing those blocks. M1 is pushing those blocks. But notice they have more mass than block 3 alone. Block 3 was 9 kilograms. This is going to be 14 plus 9, so it's going to be much more mass. And the idea is it requires more force in order to achieve the same acceleration that block 3 has. This will be called F of 1 on 2. Alright, so now we just do the math again. let's call it F of 1 on 2. It's going to be M2 plus M3 times A, where M2 and M3 are the masses feeling the force. And we'll calculate what that force is. .9 newtons. Alright, so if we go back to our diagram of the original blocks, what I want to do is show that there is now another force on M2, one that pushes it forward, and it's being pushed, to the right harder than it is being sort of impeded by M3. Like M3 is providing resistance to M2 accelerating there, but M2 is still going to accelerate to the right. So this is F of 1 on 2. But there has to be a reaction force to that as well. And it's like, who feels the reaction force? Well, 1 was the object pushing on 2. So that means that 2 is going to push back on 1 with a force equal and opposite in direction. That's Newton's third law. So this will be called F of 2 on 1. And we said it was going to be 80.9 newtons. Alright, so we can put these in. Now, since these have a subscript of x, I'm going to let to the right be the positive x direction. And so if that's the case, we want to let the sign determine the direction. So the force of 2 on 1 is a resistance kind of thing. It's pushing in the opposite direction of acceleration for the blocks. So let's put negative 80.9 for that. For 1 on 2, we just need positive 80.9 newtons. For 3 on 2, that's pushing to the left, so negative 30.6. And then for 2 on 3, it's pushing to the right, 30.6 newtons. And then there's just one more part of this to explain, I guess. And that is we can move this force that's being applied to a new location. But what's a good location for it? We want that applied force to be acting on block 1, because that's the thing the person or whoever's doing the pushing is in contact with. So let's just say it's a person out here pushing on the blocks. Then they're applying what's called force of push, or you could call it force of person on block 1. How big is that push? Apparently it is 108 newtons. So it's like a progressive thing. If you're pushing 3 blocks, all 3 blocks here, you got to push with a large force, 108 newtons. Block 1 is only responsible for pushing block 2 and 3, though, which is why it only has to push with 80 newtons. And block 2 is responsible for pushing block 3, and it only needs to push with 30.6 newtons. So the force, well, the normal force between the surface is here, like where they're in contact, it gets smaller and smaller as you move through the object. So to explain that, what I mean is a normal force is just between any two surfaces. And so the normal force at this junction between the person's hands and the block is a large force, 108 newtons, between these surfaces. I mean the hands and the side of the block. Then we're going to have 80.9 newtons between these surfaces. And we'll have 30.6 newtons between these. And at the very edge, the leading edge of the block, 0 newtons, because there's nothing in the way.